My name is ROEKMANN. I work at Utrecht University here. I'm professor for atmospheric physics and chemistry, and we study the global cycles of greenhouse gases and related components in the atmosphere. So we do that usually on a fundamental basis. We really want to understand all these details, but of course the greenhouse gases have very large societal relevance. And in the past years we have been more and more getting into the question of applying our science to solve and contribute to the challenge to reducing these greenhouse gases in the atmosphere.
That must be quite a relief for you in a way, because knowing what the severity of the problem is and working in an area where you can maybe do something about it. What are your thoughts on that?
Well, it's a relief but also a challenge, because you also realize how little can be done. There have been enormous efforts to try to reduce leakages, to reduce emissions, but the greenhouse gases are still increasing. For methane, importantly at the moment, greenhouse gases or the concentrations in the atmosphere are still going up. We don't fully understand why, but the whole scientific community was surprised when in 2007, after the methane has stabilized in the atmosphere, the concentrations were going up again. So that's also quite of I can be relieved, but I'm also worried, because we don't really understand why this is happening.
It seems to me that we're looking at a number of different methods of climate restoration or removal or conversion of methane, and that one of the biggest challenges is taking the science to scale, because the variables just increase exponentially, I guess. Can you just use that thought to lead into what it is that you're doing? I mean, you're having to sample masses of
Okay, well, we can, of course, in the laboratory, we can put an air parcel in a reactor and try to destroy some methane, and that's easy. But the atmosphere is so big, and attacking something on the scale of the atmosphere is really a huge challenge. And we have recently also discussed that in a workshop. So there are technologies, but how can we make these technologies so effective that they will actually make a difference, that there will be a decrease in the concentration of methane at the global scale. This is not only a scientific problem, it's also really a technology and an implementation problem.
Right. So leading on to that, what you're having to do is massive sample taking, I guess to look at all the variables, to understand all the variables.
And can you maybe find a way to bring in the large scale and the long-term aspect? I think that's helpful.
Yeah.
So in this project, we are now looking at the question of how we can accelerate the removal of methane from the atmosphere. The emission reduction may be one way, but acceleration of the removal may be another way to bring the methane down. It is, of course, a big question mark how that works scientifically, and at the moment our role here at the university is again to understand the fundamental questions and the fundamental processes that work. Of course, if we find this out, the question is, can it be implemented? Can be implemented at the scale, at the spatial scale and the temporal scale that is needed? It is really challenging, but maybe nature helps us. There are big systems like these big dust storms on Earth that transport Sahara dust over the Atlantic Ocean, and they have a scale, they cover thousands of square kilometers, so they may actually help us to spread out agents that could remove methane over the globe in a way that is different than a chimney or an individual point where humans may release methane. So that is actually something that could work in our favor.
If you were called to one of your kids, bring my parent in to explain what they do, could you just basically explain that, what your job entails, and in particular to the process of isotopes and everything. So, but if you could just kind of, present it to the class, as it were, the kids.
So we have the methane, a greenhouse gas in the atmosphere, and we want to see how it is removed. We are looking especially at one specific removal pathway, which is by chlorine. Chlorine is a very active gas in the atmosphere that reacts very quickly. And now, chlorine in a certain environment removes so little methane that no one can measure it. There's also so little chlorine that no one actually can measure how much is there. But the nice thing is it forms a product that is carbon monoxide. And on the carbon monoxide, the methane that is formed via this reaction has such a special signature, we call it an isotopic signature, that you can measure really very small amounts of methane that have been removed by chlorine and form carbon monoxide. So we're looking not at methane, but at carbon monoxide. We can actually find out how much was removed by this pathway. And that's what we are now trying to set up in different places of the globe. We know that this reaction happens, but we don't know how much happens in which places of the globe. That's where we go with ships and to different stations, to island stations on the globe. We take samples there and we measure this carbon monoxide and we try to find out, has now in the region, has the reaction methane reacting with chlorine, has it taken place and has it removed some methane? And if we find out where it actually works in the atmosphere, we may also find out where it could be enhanced.
And in particular, if you could describe your job in connection with this.
Well, I am mostly supervising the team here at Utrecht University in setting up the project, making the measurements, also setting up the instruments that you have seen from my colleagues, and then interpreting, evaluation and interpretation of the data. So that means, we look together. Sorry, can we stay?
Yeah, sure. No, this is great, though. This is really helpful.
Yeah.
So I have studied atmospheric processes for many, many years, and I also teach about it. So, my expertise is that I know how these reactions are actually happening in the atmosphere. So I'm supervising the PhD students, the technicians here. I help setting up the analytical systems. I importantly then sit together with the PhD students, the scientists, and try to make the interpretation and the quantitative interpretation. So what do the measurements, these numbers that we get out of our instruments, what do they tell us? And we use, for example, simulations from atmospheric models. So the models can tell us how this methane, again, and carbon monoxide, how they vary on the globe, but we may measure something different. So there will be differences, and then we want to understand what are the causes of these differences. Are these, for example, problems with these model calculations? Or are these measurement errors that we sometimes also have? Or are these really signals of the methane oxidation pathway that we are looking for? And at the moment, we are really on the hunt to find out where we can see these signals from the methane oxidation that we expect based on our theoretical knowledge. We are going to the field now, to the atmosphere, and trying to find these signals so that we can really pin them down and say, this process is really working here.
Can you compare the projections to the findings that you're having? What's your thought? What's happening there?
Well, at the moment there are very few projections on this chlorine chemistry. There are only uncertainties. In all recent publications, this has been, the reaction with chlorine has been identified as one of our large uncertainties for the methane budget. And this intends especially, or this refers especially to this isotopic composition that we are measuring. So a special isotope signature or isotope effect that is very strong in the reaction of methane with chlorine. And we don't know at the moment how large the removal of methane by chlorine is in the atmosphere. So we want to find out how this is. So I would say there are no real very good projections. It is more an uncertainty in the scientific field that we are trying to close.
Okay. But the results that have come in so far seem to kind of support the hypothesis. Huh?
Yes. Qualitatively and I would say semi-quantitatively, we now see that where we expect these effects to happen, there are signals. And as a scientist, you want to be sure that the signal is really caused by this process and not, again, an artifact of the reference or an artifact of the model or an artifact of our instrument. So we want to have several of these events and identify it and understand them before we can then really say this effect happens.
Okay. And just on the equipment itself, I mean, it looks pretty impressive to me. Could you just talk about the complexity of the equipment that you're working with and its uniqueness, if it is unique?
And maybe something about precision, or do you think we've covered precision adequately with Martin and Karina?
I think they've talked, Yeah, but I mean, it's fine to duplicate it, but basically, it's as I say, it looks very impressive, and that's what you need, I guess, to be able to measure to that degree.
Yeah, so the challenge that we always have in our laboratory, we make these measurements of the gases, and we measure the special isotopic composition. And to do that, we have to separate one gas, whatever gas it is, in this case now carbon monoxide, we have to separate it from all other gases. But there's only one molecule in 10 million molecules is carbon monoxide. So we have to get all the other 10 million molecules out and only keep the carbon monoxide molecules. That is quite a challenge. So we really have to clean the carbon monoxide extraordinarily well. That means we have to remove all other compounds like the oxygen, the nitrogen, the CO2, the water, also other greenhouse gases and contaminants. And this is the really challenge to the analytical system. That's why it takes us years to build such a system, to really purify one sample of one certain gas. And we do that for carbon monoxide, for methane, for the laughing gas, or for hydrogen. So we have different systems for each of these gases. When these systems are running, they can be very precise because we do the mass spectrometry. So we look at the different masses of the different molecules than the carbon monoxide molecules. And by using these techniques in quite big machines, as you have seen in the laboratory, they are quite robust. We can measure the sample for a long time, and that means that we can get a really high precision. So we can measure these very small differences in carbon monoxide and its isotopic composition, which allows us then to find out how much methane was removed.
Right.
Can I
Yeah, so we have analyzed data that colleagues took several years ago, and we found quite strong variations in the signature that we are measuring, and we think this is the signature, this is the smoking gun for the methane plus chlorine reaction. Since these measurements have been done 20 years ago, we are still a bit reluctant to say it is it, because, well, we want to repeat this now. We want to do it also with our current understanding, with our current machines, with our current modeling expertise that we have, and we want to also bring in satellite observations that we can see where the dust is coming in and really confirm that this is the process that's working. So at the moment we are trying to, confirm and really, make the gun even more smoking, really say that this is the process that causes these variations. Because again, we cannot go back 20 years in time, we cannot really guarantee that an instrument in the laboratory didn't have particular noise in a certain period and created some signals. Of course, the group that did these measurements is convinced that it wasn't the case, but it's always good as a scientist, it's always good to check. We need to be critical, especially when we are talking about a potential intervention of the climate or the atmosphere, which could have quite some large consequences. We really want to make sure that we first understand what is going on.
What about time, risk, and urgency? Because we're just getting warmer and warmer and warmer, and methane certainly seems to be a pathway that could at least give us some breathing space. But equally, as you say, we've got to be so certain. But we're in a rush. Can we? Is there a way to reconcile that?
Especially with the fact that there's a danger of having results that give the wrong direction.
I think there's a big dilemma at the moment. We want to act as quickly as possible, but we also need to make sure that before we implement something, we understand the consequences. You don't want to end up in a situation where you put a lot of effort into a technology that either doesn't solve the problem or creates even another problem somewhere else. And I think at this time in the world, we are of course under pressure, but still not under so much pressure that we want to risk also in the terms of social acceptance, right? You cannot really start tampering with climate before you have understood the consequences. It will kill such a project if you do it too early and end up with some consequences that are actually not beneficial that are at least not understood and accepted as being potentially also adversary.
If you had to speculate how long the process is going to take, the work that you're doing, and to get to the conclusions, not categorically, but to get to enough level of confidence. How long do you think that's going to take, if you had to guess?
Well, we are putting quite a lot of effort into this now because we also see the urgency. So I think within a year, we will really be sure about the mechanism and its relevance to the atmosphere and the real world. Then the question is whether an anthropogenic or human enhancement of these processes will work. And that may still take some more time to find out. Probably you would try to do it first in a pilot study at a certain location where you don't have any adverse effects. And that may still take, well, it would need to be implemented in some regions. My colleagues that you have talked to are now working also to find out in which regions we would actually carry out such a study. And I strongly want to also support this, that within 1, 2, 3 years we would actually be at a level where we can decide on whether such a process would be implemented.
That's great, thanks. Oh, and I don't know if he asked you this, but I mean, how do you personally feel about the state of the climate and moving forward and the legacy that will be left for kids and the problems of, Paris Accords and stuff, and governments come and go and they renegotiate and then they pull out and then they go back. What are your thoughts on all of that?
I'm personally worried. I'm also thinking that the problem is not taken seriously enough. This 1 degree more or less, that sounds so little. But if you're now talking about 2 or 3 degrees, if you consider what that means in a couple of years, that, well, maybe the warm days will stay as warm as they are, but the cold days will maybe 10 degrees warmer. So there will not be cold days anymore in the summer. So the whole prospect, is not taken seriously enough. You see that with other societal issues like the COVID pandemic or wars, there is money available, there is action available, things can be done, but it's not implemented the same way, or the climate crisis is not assessed in the same manner or addressed in the same manner as these other crises that we are facing now, which I think is an error and short-sighted, because in the end, the future generations will have to pay the price for that. And it's not, it's not going fast enough. All this implementation of climate action is not going fast enough, even in the developed countries, where you may have even governments that are supportive to it, but even in these locations, the goals that the nations have set are not sufficient to reach this 1.5 degree goal, for example. So then extrapolating this to other parts of the world, where the realization of the problem may be much lower, that worries me. It's not going the right direction.
That's great, thank you.
You don't need a short version of that.
I can edit it down, but let's just try one short, succinct.
Okay.
But,
and I don't know, you rightly mentioned the number of cold days is greatly reduced. Maybe just say something about that in terms of food security, the fruits and apples.
Yeah.
So just a note, just a top level, this isn't going well, or however you feel,
Yeah.
Well, climate change is not evolving well at the moment. The actions are not strong enough, quick enough to mitigate it. We already see now how it affects lives of people, food security, water availability. I have to stop watering my garden probably in a week or two, because it will be too dry even here in the Netherlands. So I think the climate is not on a good route, and the action is not fast enough.
That's great.
On the other hand, if we manage to implement the right policies, if we reduce the emissions, if we stabilize the climate, we will all benefit, because we will get rid of technologies that contaminate the earth at the moment. So we will make the world a better place.
Yeah, that's great.
And not just stabilizing the climate, but actually reducing CO2 and methane in the atmosphere.
Good.
So
let's do that one more time.
Yeah, exactly. That's right. But if we actually manage to reduce greenhouse gas emissions, to avoid warming and actually avoid Sorry, again. But if we actually manage to reduce greenhouse gas emissions so that climate doesn't warm up so much, it also means replacing technologies, contaminating technologies with much cleaner technologies. In the end, the world will be a better place.
Yes.
I think that's still just on mitigation, and I guess what our film is about is removing carbon from the atmosphere.
Okay.
So
Should I? But if one of our technologies that we are working on here is actually successful, and we manage to take greenhouse gases actively out of the atmosphere, reducing emissions, but also reducing what has already been emitted in the past, we will make the world a better place.
I know it feels ridiculous and awkward, but it will look good. Okay, and just keep one more time. That's great, yeah, thank you.